All right, good, that works. All right, so I'm going to talk about structured correlation matrices. A bit of background, so I work at this advertising agency called Omnicom Media Group. I actually don't do much modeling anymore at my current job, but I used to do a lot. And this problem started actually at the last 2 StanCons ago, the one that we had online, or maybe 3. So probably about 4 years ago. I was working on this model, and we had this big correlation matrix. And we wanted to, put some block structure in it. It ended up being too difficult, so we actually just left it unstructured. But I kept thinking about this problem, and it wouldn't go away. And so this is, I would say, about 90% of the result. Great. All right, so what is a correlation matrix for some of you? So it's symmetric. It has to be diagonal, like ones along the diagonal. Off-diagonal elements are between -1 and 1. And it's positive semi-definite. So what is that? I think the first 3 are pretty self-explanatory. And the last one is the tough one. And it has this property, and there's a bunch of other things that go with it. We don't have to spend too much time on that, but that is really kind of the key here that makes it difficult to model these things. And why, what is so difficult about this? So I have this samosa here, and this is just a 3-dimensional correlation matrix, but that is the space of valid values within that 3x3 matrix. So what ends up happening is actually as you increase the dimensionality of the matrix, that gets smaller and smaller and smaller. So if you have a really big correlation matrix, actually the probability of generating a valid positive definite matrix basically goes to 0. So you actually need to construct it such that it is always positive definite. And then what is a structured correlation matrix? It's anything with structure. Okay. Of course, it was either Monty Python or Trump, so I figured I'll put a Monty Python quote. And I'm not actually going to talk so much about different structured correlation matrices. I'm going to talk about how one might code structured whatever structure that you want. So it's actually a more kind of general thing than that. And so really what I mean by structure is you can put block structure. You could put known values in. Zeros are a common one. And then some other types of structure that you might see in some models. So you have all the same elements, toplets, so on and so forth. So I just already talked about that. All right, in Stan, we have 2 types of these. So one is just the correlation matrix itself, and then the other is the Cheski factor of the correlation matrix. The Cheski factor is used because it's smaller. It's half the size, so it's just lower triangular, and it makes it much more computationally efficient to do a bunch of things. Plus, there's a bunch of nice properties that make it faster to do inverses, which we have to do a lot. And then the diagonal is basically, you can use that for the determinant. So it really simplifies a lot of the calculations by having it on this. And so it would be nice if we could just parameterize it in terms of that, and then we can get out our actual correlation matrix just by doing the cross product. I'm going to put down here another thing, which we don't have this type available in Stan like the library, but underneath the hood we use the eigen library, and we often use the LDL decomposition, which is basically the same thing, except that it avoids a square root in the diagonal. So the diagonal is just the D is a diagonal matrix, and it is the square of basically what is up above. And that actually is really nice. And it's more stable, and it has some other things. And I've actually parameterized it in that as well. So I can share that later. All right, so I'm not going to, well, I think I should maybe go down a bit. All right, so I do have some code, which might be, hopefully it's not too bad. So I didn't put the C++ code, but this is roughly what is done under the hood for the Cheski factor of correlation matrix in Stan. We call it stick breaking, and you don't really have to understand everything here. I'm just kind of wanted to show it to see what it does. So it breaks this stick, and that's like you have a unit length stick, and you kind of break pieces off at any given time, and then you multiply it by like something between -1 and 1, and it gets out, and then you subtract the stuff from the stick, and you do that a bunch of times. So one of the nice things about the Cheski factor on correlation matrices is that each row, if you're talking about the lower triangular version, is a unit vector. So it has this nice thing, and so that's kind of uses that. So I want to give a motivating example, and actually there's a guy in here, a bloke, you might say, who who actually, he was the one who got me to really work on this. So I actually finalized this in the spring, and he's up there, Enzo. I saw him somewhere. Oh, there he is. And he had this problem, and he contacted me, and he was like, I need all positive values in my correlation matrix for my problem. And he's like, this code that you had on the forums, it doesn't give the uniform matrix on positive values. And I'm like, okay, so why is that? So I'm gonna show you what happens if we use the Stan transform, and we just make it so everything is positive. This is like what you would naively do, and this is what I had first done. So I'm just going to transform everything into 0, 1 instead of -1 to 1, okay? And then, well, here I rejection sample, so you can see what we should get. So we should get something, and this is, I think, an LKJ of 4 is the prior. And that's a uniform prior on these correlation matrices, which is a whole nother interesting topic. But basically, every value on that correlation matrix for an LKJ of 4, the mean should be about 0.28, and we should have a standard deviation of 0.18. These intervals, you're gonna, if you have an eagle eye, you'll see in the next thing that they're gonna be a little bit different. I was too lazy to change the interval, but also Julia, they do slightly different stuff with their HDI versus what we do in R and stuff. So anyway, so don't pay attention too much to that. So these two. All right, but this is what Stan gives. As you can see, it is not uniform. Okay, so why? Why isn't that uniform? I mean, so the Jacobian is right. I did that right. Everything else follows. So it's not a Jacobian problem. All right. So I will get to the reason why, but we're gonna go a little bit more in depth into Cheski factors. So this guy, Andrei Cheski, I actually tried to read the original paper. It's almost impossible to find. But he died, I think he was 42. He was in the army, and he just came up with this method. I think he was in the army. He was doing like geophysics or something. I don't know. Smart guy. Unfortunate about dying so young, because who knows what else he would have done. All right, so this is, so C, if I take C as my correlation matrix, and I break it into the Cheski factor, this is basically how it comes about. So actually the first column is your first column from your original correlation matrix. Really nice. And then you can see how the rest, okay, it kind of breaks up, and then that's like that stick breaking thing. So it's, okay, all the rest of the stick. And so that's just the equation to make it a bit more condensed. Now, let's do something to this, just for fun. Let's rearrange that stuff. because I've never seen anyone do that. And let's add some lower and upper bounds that maybe we want to specify. All right, cool. Let's put the stick thing back, okay, because we need to take care of that. All right. Hey, we have now this thing. Well, what's really neat about that equation right there is that it gives us the bounds, and all we have to do is put it in an upper and lower bound transform, and that's the Jacobian for the matrix. So every value, you just do that. Okay, you're good. It's not complete, though, so I don't know. Some of you may be mathematicians, and you may have been like, I don't think that's going to work. And you're sort of right. So and this is just a very small example, so if we have a 3 by 3 matrix, and we want all negative correlations, let's say, and we set C21 and C31 to a valid value, right? Negative 1 over the square root of 2. There's a specific reason for that. And we solve for the bounds. Well, what ends up happening is we want the bounds to all be negative, but that implies that the bounds must be positive. So that's what that's saying. So you literally have to be very careful about the bounds, and you have to be able to kind of know what your future bounds are to know what you can have, unfortunately. All right, so this is the stand code for that thing. I'm not going to go too much into it. And I want to show you that when we do it now, hey, 0.28, 0.18, it works. So hey, look at that, it works. We have this method, and we can constrain correlation matrices. I've got a few minutes, so let's do a very motivating example. So in this case, I have zeros there that I want, and I want these other values to be between negative 0.8 and 0, and 0.3 and 0.7, and it works. So now my correlation matrix has everything else is like whatever, and those values are estimated, and I ran this yesterday, last night, and that's what it is. And so you can see that we have our zeros, great, and then we have this thing, if you look at the interval, it is all negative, and this one is 0.3, 0.58, so it has those bounds. So that was a nightmare to code up. So yeah, the next stuff, I do have an LDL parameterization. It is more stable and really cool, so we could literally have an LDL type in Stan if we wanted. So I have derived like 6 pages of inequalities to make sure that the values with the bounds looking ahead, I haven't wanted to code it up. I probably had that paper for like, I don't know, 5-6 months, and I haven't tried to code it up and test it. So if anyone wants to work on this problem, I'm kind of getting to my limits, shoot me a note. And then, let's explore new priors for correlation matrices and things that can use this method. And then I did post a note, so if you want a bit more about the math and stuff, it's in that archive. Thank you.
So we have plenty of time for questions. And while we ask questions, I'm going to ask Adam to set up.
Wait, is there any question about any of the code? Anyone want to see anything before he sets up? Yeah. No. Okay. Great. So you can go ahead. Yeah. Brian, sure.
Just quickly, can you kind of give an intuition? I can understand why I might want like a 0 in a certain place, like in a correlation matrix. Does that mean that I can put it in that place in Cheski? Like, I don't think I fully understand.
Yeah, I know. I had to. Yeah, so it's all parameterized in terms of the Cheski factor. So what's cool though is that if you put in like an index, it will translate like back into the correlation matrix. So in the code, so it's like you only have to think, because it's impossible to think about the Cheski factor. That's kind of neat about it. Yes.
Could you give a quick introduction to the current landscape on prior elicitation for these things?
There's not too much. I'm working on some stuff actually. So the LKJ thing is really interesting. I actually was talking to Seb, and I have the C-vine parameterization, and actually if you look in that parameterization, you can put beta, shifted and scaled beta priors on each value. The thing about LKJ, and the reason why it only has one parameter, is that if you do it in a very specific way, all the math kind of works out to only have one. But if you want different priors, if you want to put different values on each, you can actually in that code. So I think that would be really neat. So I want to like give that to people and let people know more about that stuff. Paul.
So I think it's really great that you figured this out. I think this will make a lot of people happy. I was wondering, some people, for example, in the RMS have requested that we I don't know, do distributional regression on the correlations. And I've always pushed back because I didn't know how to constrain it to make the whole thing positive definite. Do you think your approach could help?
So I will have this big caveat that like you have to increase get the LKJ. So you have to kind of regularize the values of it. So if you, that example where if you had like -1 over the square root of 2 and it like didn't satisfy the bounds, that happens as you get like larger values that come into the matrix, which is why I'm working on like the bound stuff. So yes, it would work like in theory, but I think if you were to test it out, you would notice a ton of divergences and all this stuff because it would like quickly hit those bounds. So there's still, I think, a lot of research in code to be done to like make that very stable and user-friendly.
Were you going to tell us why the rejection sampling didn't work?
No, the rejection sampling worked. Sorry, it was the stan thing that didn't work, and yes, I will tell you. So there's a very specific geometrical reason, but at the end of the day, it's just that the Cheski factor itself, if you have, it's like there's a dot product basically in it, and if you take the product of two negative numbers, you can get a positive number. So if you constrain all the Cheski values to be positive, you actually are limiting the number of valid matrices that are positive that can happen, and so it's wrong. It's like, it's literally wrong, but wrong for a very interesting reason that we typically don't encounter in probabilistic programming.
Actually, I recall that priors and correlation matrices are super interesting, let's say, and I actually remember asking Ben Goodich about what he would do. So what's your thought on this? He suggested to use Wishart priors on its centered on some variance, on some covariance matrix, which are, what you basically gravitate to.
Yeah, I think, so funny enough, we've gone away from Wishart or Wishart priors, and now I think there is a case for them in that when you have specific things that you know or historical information in your case that you could use here, and I think there is possibly like a generalized Wishart kind of thing that would take into account even the structure that we could derive. So that's like, that would be cool. And then you could use that, and you could have, this like prior within there that's positive definite, and you could literally construct your positive you could force it to be positive definite with this, and then put it in there, and then just have, the matrix come out.
So let's thank Charles.